Hi there, I hope you are well. Today's lessons is focusing on part 2 of shear and bending moment in beams. The study of the bending load is complicated by the fact that the loading effects vary from section to section of the beam. In this video, we shall discuss the relations existing between the loads, shears, and bending moment in any beam. A beam is a bar subject to forces or couples. So a beam may be determinate or indeterminate. Statically determinate beams are those beams in which the reactions of the supports may be determined using the equation of static equilibrium. They may be, for example, simple beam, cantilever beam, overhanging beam, as I said before in the previous video. For simple beam, a simple beam is supported by a hinged reaction at one end and a roller support at the other, but is not otherwise restrained. A cantilever beam is supported at one end only with a suitable restraint to prevent rotation of that end. This is the cantilever. And the overhanging beam is supported by a hinge and a roller reaction with either or both ends extending beyond the supports. Their reaction for statically determined beams, the reaction can be determined directly from the equation of static equilibrium. And statically indeterminate beams, when the reaction exerted upon the beam upon a beam exceeds the number of equations of in static equilibrium, the beam is said to be statically indeterminate. Like this prop beam, fixed or restrained beam, or continuous beam, when the number of reaction exceeds the number of equation in static equilibrium. More example of statically indeterminate beam, like the prop beam. Here we have one reaction, R1, R2, and moment, and only two equations available, summation moment and summation Fy can be used. Thus, the beam is indeterminate to the first degree. More example for statically determinate beam and statically indeterminate beam as shown in this figure 4. And types of loading, we have loads applied to the beam may consist of concentrated load, uniform load, uniformly varying load, or applied couple or moment, as shown in figure 5, types of load. Look at this simple support beam. Let us discuss the internal forces caused by the applied load, and if the cross section of the beam is I section as shown in this figure. The simple supported beam shown is supported by hinge and roller, and there is applied load here. So we have reaction R1, and this one will be 0 because no horizontal load, applied load, and we have a reaction R2 at the roller side. If we if an exploratory section taken, the cross section of the beam as this figure I section, the internal forces will be either internal shear forces vertically oriented in vertical direction, and internal normal forces which is oriented along the axis of the beam. So, to sum up the previous slide, the internal forces is developed within the beam to maintain equilibrium. These internal forces have two components. We have internal shear force oriented in the vertical direction, and we have internal normal forces which is oriented along the axis of the beam, as shown in figure 6. And the internal forces in the beam, the resultant of the internal shear force would be like this. And the resultant of the internal normal forces, if the beam sustain a positive moment, so the sagging of the beam will cause compressive at the top fiber and tensile at the bottom fiber. And the resultant of the internal normal forces will be a single moment in this direction, counterclockwise or anti-clockwise. So at any exploratory section, we have shear force and bending moment, maybe in different direction, not only in this direction. So shear force, which is resultant of the internal vertical forces, and bending moment is resultant of the internal normal forces. This is the section of the internal forces in the beam. In calculating, we have a sign convention for shear. Look at this simple support beam on these two section taken for positive shear. Tends to move the left segment upward with respect to the right, as shown here, and vice versa for negative shear, as shown in this movement. This is the original beams. With this movement, it is negative shear generated here. For moment, sign convention for moment, sagging moment is positive. If that's the beam, I will put this face as, and this is the deformation of the beam. This is the smile face. So sagging moment is positive, or remember, smile face. So any moment causes smile face or sagging is positive moment, and any moment, hogging moment, is negative for sad face. So in calculating shear force, upward acting forces or loads are considered as positive. So as I said, in calculating shear force, upward acting forces or loads are considered as positive. So a positive shearing force tends to move the left segment upward with respect to the right, and vice versa. You can double check your textbook in pages 108 to 110. The slope and shape of the shear force diagram are determined by the corresponding load intensity, and the slope and the shape of the bending moment diagram are determined by the corresponding ordinate of the shear diagram. So dv over dx equal load. So change in shear force between any 2 points are area under the loading diagram between 2 points. and the change in bending moment between 2 points or any two sections equals the area under the shear force diagram between 2 points. So dv or d over dx is the slope of the shear diagram, and dm over dx equals shear is slope of the moment diagram. So the slope and the shape of the shear force diagram are determined by the corresponding load intensity. So slope of the shear diagram related to the load intensity. Slope of the moment diagram related to the oriented of the shear diagram. So from load we calculate shear force, then we calculate or measure moment, bending moment. Illustrative problem. Look at this simple beam, 4 meter long, with applied load of 12 kilonewton at the mid of the beam, mid span. So to start with, as we said before, AB and C are called change of load points. A, B, C are called change of load points. Very important to determine or write A, B, C at these positions. First of all, we need to draw a free body diagram to compute the reactions by applying summation Fx, summation Fy, and summation moment. So we have three reactions. By equating to 0 summation Fx, this yields that A sub x equals 0. And by equating to 0 a summation moment above C, and the clockwise direction is positive, this yields A sub y equals 6 kilonewton upward. We next equating to 0 summation Fy. This yields that C sub y equals 6 kilonewton upward. Now we are ready to draw the shear force diagram. We plot 3 lines along the change of load points A, B, and C. Then horizontal line for shear force diagram, upward positive, downward negative. We start from point A. The upward reaction of 6 kilonewton at A causes the shear ordinate at A to increase to 6 kilonewton. And between A to B, the intensity of the load is 0, and the corresponding shape of the shear diagram is 0, horizontal line. At B, the concentrated load of 12 kilonewton change the shear ordinate to minus 6 kilonewton. Minus 12 plus 6 equal minus 6 kilonewton. The area between B to C, the intensity of the load is 0 as well, and the corresponding shape, the corresponding slope of the shear diagram is 0, horizontal line. At C, the upward reaction decrease shear ordinate to 0. Now for bending moment between any two sections, and we need to calculate the area. So bending moment between any two sections equals the corresponding area of the shear diagram. So we have area 1 and we have area 2 in minus. So to start, we draw a horizontal line This is bending moment diagram. Plus, up, down, minus. The bending moment is 0 at A, and the bending moment at B is given by area 1, or area 1 equals 6 kilonewton times 2 equals 12 kilonewton meter. We draw a point. We said the bending moment at B is given by area 1, and it equals 12 kilonewton meter. So we draw a dot or a point to show the 12 kilonewton under B. And we draw a horizontal and a straight inclined line from A to B for intervals of uniform shear intensity. So we say the slope of the bending moment generated or related to the shear. Because we have here a uniform shear intensity, so we get either upward or downward movement of the shear slope for this part. Similarly, the bending moment as C is equal moment at B plus the delta moment between B and C, which equals area 1 plus area 2. For area 2, the area equals 6 minus 6 times 2 equals minus 12 kilonewton meter. So plus 12 minus 12 equal to 0. So we go back to 0 at C. And the slope will be straight inclined lines between B to C, because the shear intensity is 0. Sorry, the shear intensity uniform between B to C. We have a uniform shear intensity. We draw an inclined straight inclined line between B to C, because the shear intensity uniform, we have uniform shear intensity. So the final bending moment for this beam is positive, so we will get a sagging deformation. Next, illustrative problem for simple beam with uniformly distributed load. Yes. Again, a simple supported beam with uniform distributed load of 12 kilonewton per meter. We need to draw the shear force diagram and bending moment diagram. As we said, A and B are called change of load points. We start from by computing, by drawing the free body diagram for the beam, applying equation of equilibrium, static equilibrium to determine the reactions. So by equating, so AY, AX, and BY, reaction need to be calculated. So by equating to 0, summation of X, this yields that AX equal to 0. And by equating to 0 summation moment, sorry, the resultant of the distributed load equals 12 times 4, 48 kilonewton downward. So by computing to 0 a summation moment about B, AY equals, that this yields AY equals to 24 upward. We next computing equating to 0 summation Fy. This yields that B sub y equals 24 kilonewton upward. So to draw the shear force diagram, we draw lines at the change of load points at A and B, horizontal line for shear force diagram. The upward reaction of 24 kilonewton cause the shear ordinate at A to increase to 24 as shown. Between A to B, the intensity of the loading is not zero because it's distributed load. So we will get straight inclined lines for intervals of uniform load intensity. Now we have intervals of uniform load intensity, so we will draw straight inclined line for intervals in which the load intensity is uniform. So straight inclined lines for intervals of uniform load intensity. And we have 24 minus 48 will be minus 24 at B. Again, at B, the upward reaction decreases the shear ordinate to 0 backward, as shown here. We have 24 upward. Again, to draw bending moment between any two sections equals the corresponding area of the shear diagram. So to start with, we need to know that positive up, calculate area 1 for the bending moment between A to B and area 2 between between A to the midspan and between midspan to B. The bending moment is 0 at A. And to calculate the bending moment at the midspan, here we need to calculate the area because we said the bending moment at between any two sections equals the corresponding area of the shear diagram. So area 1 equals area of the triangle. Put the point. So because of the shear diagram, it is straight inclined line from the first degree. So that will produce a second degree curve for the moment. To draw that second degree curve, we need to know where is the zero shear. We draw straight line, horizontal straight line, on the second degree curve between 0 and 24. Can be like this or like this. The correct one is the black one because I need the tangent to the moment curve at the zero shear force. At the zero shear force, the tangents to the moment curve with the horizontal line. So thus dotted red line curve is ignored. Again, the moment between the midspan and B equals the moment at midspan plus area 2. So area 2, same area 1 times 2 times 1 over 2 equals minus 24, and similarly the bending at B is moment at midspan plus delta moment between midspan and B, and equals area 1 plus area 2, and it is 24 minus 24 equals to 0. Now again, this part of the shear force is non-uniform or varying shear force from the first degree in inclined lines. So we said bending moment come from integrating the shear force diagram. By integrating first degree, we get second degree lines or curve. So again, we have two options to draw this second degree curve, but we should follow the same steps for this part. Where is the position of the shear of the zero shear force here? We draw horizontal line. We need this second degree curve tangents to the straight line. So we have one option, or this curve tangents, or the lines tangents to the moment curve. I hope this helped to understand how to draw the second degree or producing second degree curve. Here is positive, minus, bending moment. Again, this will deflect like this, because this is positive. It is positive moment. From the previous video, I solved the overhanging beam, and some students asked for more clarification. So please follow these steps. Again, equating to 0 summation of x. Before that, we draw a free body diagram, and from free body diagram we got RB and two reactions, B and RD. Equating to 0 summation of x, we get no horizontal forces at B, and equating to 0 moment around D. This yields reaction at B equals 56. This, then equating the to 0 the summation of y, this yields that R sub D equals 24 upward. Then we are ready to draw the shear force diagram. As I said before, the upward reaction of the downward reaction at A, the downward reaction of minus 30 at A causes the shear ordinate at A to decrease to minus 30. This is the shear force diagram axis, positive, minus. This is the 30 downward. Then between A to B, 0 load intensity, horizontal, straight horizontal line. Then at B, the upward reaction of 56 kilonewton causes the shear ordinate at B to increase to 26, because 56 take away 30 is 26. Between B to C, 0 load intensity, horizontal, straight horizontal line. At C, the 50, the external load or the applied load causes the shear ordinate at C to decrease to minus 24. Then between C and D, zero load intensity, horizontal, straight horizontal line. Then at D, the concentrated load, the reaction of 24 change the shear ordinate to zero back to zero. For moment, so load intensity, the shear related to the load intensity. To draw the shear, to draw the bending moment diagram, we start to calculate the shear, the bending moment diagram at A equal to 0. Then the bending moment at B is given by the area 1, or the area between A to B of the shear force diagram, which is 30 times 130. We put a dots here and we draw straight inclined line for uniform shear intensity. Then from B to C, again we have a uniform shear intensity, and the area and the shear at C equals, the bending moment at C equal the bending moment at B plus the area between the shear, or the delta moment between B and C, which equals the area of the shear between B to C. So 26 times 3, 78, plus minus 30 equals 48. And because we draw a straight inclined line for uniform shear intensity. Look at this again. Finally, the moment at D equals the moment at C plus the delta moment between C and D, which equals the area between C and D of the shear force diagram. And the area of the shear force diagram between C and D equals 24 times 2, 48, minus 48. So 48 minus 48 equals to 0, and we will draw a straight inclined downward, because this is minus, downward to 0 again back. As I said before, at zero shear forces, we got maximum bending moment, maybe in minus or in positive. Go to pages 130, 136. This illustrative problem, sketch shear and bending moment diagram for the beam. Just double check your. And for self-study, independent study, homework, beam loaded as shown in figure 13, sketch shear and bending moment diagrams for the beam, and is a required homework in class work for shear and moment part 2 on Google Classroom platform. For your kind attention and further action, thank you very much.